Here we'll talk about dimensionality reduction. Recall the course is built around these 6 core learning objectives, and we've talked a good bit about the math behind these techniques when we're talking about distance or we're talking about centrality. Well, we're going to talk today about some of the unsupervised techniques for doing what's called dimensionality reduction. Recall from last time, what we were trying to do was evaluate the similarity between two elements. So we talked about the math for doing different kinds of distance metrics or similarity metrics like Euclidean distance or cosine similarity, edit distance, etc. This time we want to talk more about how we can make these data sets, which could potentially have many features or many columns of information associated with a given sample, into a more tractable form. We talked about this already in some degree using menhash that gives us a way to reduce the dimensionality or reduce the number of columns in this data or compress it in some way. Now what we want to talk about today is connecting these lower dimensions with some latent structure or some sort of deeper information in the data. So you might think of this as genre associated with movies or styles associated with text or books. So learning objectives for this week, the first one focuses on connecting this idea of dimensionality reduction to this latent factor idea, or the idea that there is latent structure in the data that dimensionality reduction allows us to get at without having to have the very large scale data that is expressing all of is the expression of these latent factors. So for example, in genres for movies, there's this idea of genre actors, where actors don't generally branch out into many different roles or many different genres of film. That's not always true, but you could think of this as a general rule. So if we were trying to group movies into clusters, we could do this in the full actor space, but maybe we want to do this in a reduced space that allows us to reduce the size of the data on disk or reduce the size of our representation of the data while still keeping something about this idea of genre structure. Now, not all dimensionality reduction can be thought of as extracting latent factors, but this is one way to think about certain kinds of dimensionality reduction, and that we'll talk about. And then we'll talk about 2 different ways to do this, primarily using PCA or principal component analysis and singular value decomposition. Looking first at defining this connection between latent factors and dimensionality reduction.
Core motivation we've talked about several times over the past few weeks is about making the web more useful by grouping content. Now we've talked somewhat about what these groups are used for and how they can be useful, but let's talk a little bit about what this idea of grouping means. So in a very high level case, when we talked about clustering, we've said that these clusters should represent similarity where 2 objects in the same cluster share some sort of real-world relationship. Now, whether that means they're things of the same genre, people of the same political persuasion, products of the same kind of category on a shopping portal, or food from similar kinds of takeout, it's not specified what that similarity means, but these are all ways where you might group things into sets of similar kinds of items. And there can be very many different ways to group based on your particular needs. Like I said, we've seen this before with the retweet graph, where we can very clearly see 2 separate groups of political persuasion. We've talked about the different kinds of Jaguar, so that based on this kind of construct in the graph, we can imagine that things up in the upper left are automotive, not all about Jaguar the vehicle. There might be Lamborghini or Honda or Ford or whatever in this space. Whereas here on the right, that's maybe a lot of software discussion or a lot of software products. And here in the bottom are about animals. So these clusters all represent some kind of connection among these items in our data. So in some sense, if we have some adjacency matrix that we want to use to extract some clustering, we have this potentially large matrix that is square in the number of nodes in our data set, and this mechanism of clustering, or this approach for clustering, drops the number of different features that we have, rather than all the features being all the different nodes in the graph. We can say our features can be what cluster you're part of. So now we have a new matrix that's n by c, and this number of clusters is definitionally can't be larger than n, and almost certainly going to be much smaller than n. So this is already some dimensionality reduction technique that we've employed just from clustering, going from the full adjacency matrix down to the cluster assignment matrix. If you've done natural language processing, you may have seen a similar kind of idea with topic modeling or latent Dirichlet allocation, where you have some matrix of documents and the words that appear in those documents, the shingles that appear in those documents, like we talked about last time, and we reduce that into a set of documents and topic maps or topic assignments, which topics appear in this particular document. And again, the number of topics are generally much lower than the number of words, so we have smaller space or smaller feature space to deal with in this new construction. So in some sense, you're already familiar with the idea for dimensionality reduction, that these groups, these clusters that we're working with, capture this hidden relationship or some set of hidden relationships among items or among documents or elements in our data set. So we call these hidden relationships latent relationships, or latent factors, or latent features. We may not know what these latent factors are a priori, or maybe you do, depending on your particular context. But I want to walk you through an example of where this is useful. So a common question that comes up in political science is trying to infer the ideological position or political preference of an individual. And it turns out from politicians' behaviors on Twitter, you can do this very easily with the news they share, that a particular politician's choice of using the New York Times versus some other news source is actually pretty indicative of their political persuasion. And we see this is pretty common across a number of different politicians. Elizabeth Warren sharing Vox, Lisa Murkowski sharing Reuters, Cory Gardner retweeting something from The Hill, Elizabeth Warren tweeting something from Act Blue, Murkowski tweeting something from CNBC. We can actually use these domains as features when we're trying to characterize these politicians. So Elizabeth Warren, you might expect, is much more likely to share content from Vox or New York Times than she is to share content from more conservative sites like Breitbart or Fox News. Lisa Murkowski is a Republican, is much more likely to share content from Fox News. Maybe she'll share some content from Reuters, but almost certainly not likely to share content from Vox or HuffPost, generally liberal media sources. Whereas Bernie Sanders may share content from much further left-leaning or liberal sources. Now, we don't really know what exactly that says from a latent factor perspective or like a hidden feature kind of perspective, but you could imagine that if you look at some really high dimensional cloud where the dimensions are the domains that you share, that politicians who are conservative are kind of going to group together in some space, and politicians who are liberal are going to also group together in some other space. And in these two clusters, there's some cluster center, and we can project some line or draw some line between these two cluster centers. And then we can project these individuals down onto this line and end up with a essentially one-dimensional projection of their political persuasion or ideology on this one line. And there's a lot of work that's gone into this to show, based on your domain sharing, you can project into this line, and we can actually evaluate your political position relatively well. Whether you're sharing Vox, New York Times, NPR is going to make you, or is more likely to associate with somebody who's liberal, whereas if you're sharing content from Fox News or Conservative Review, you're more likely to be of a conservative persuasion. And in this case, ideology clearly is a latent factor and is intrinsically linked to a person or politician's choices about which news to share. As naturally, if you are a conservative politician, you're going to share news content that is sympathetic to or more in line with your political persuasion or your political agenda. Same if you're liberal, you're going to share content from liberal sources that's more in line with your agenda on that side. So this is some natural sort of link here between political persuasion. Now, this means that you can decompose your choice of news sharing into this single dimension, or maybe some handful of dimensions that's linked with the political ideology, and you get this nice potentially summary statistic that would then be determining which domain you're or news source you're likely to share. So you can come up with somebody else who's shared other news domains and then say, well, where in this space are you? Which news domains are you likely to share? You can do that for recommendation or identify how close to people are based on political persuasion and a number of other things based in this lower space that makes a lot of analysis easier. Now that doesn't mean that all of these sort of latent factors are informative in the sense of they tell us exactly what's happening or they're easily interpretable. So from the standpoint of ideology, this is an easily interpretable thing, right? We can very clearly see that people who are far left on the scale are more likely to share liberal sources. People who are far right on the scale are more likely to share conservative sources. In the same way, if we look at topic models of words and documents that are shared, these topic models put words into groups, and sometimes these groups are very clear in terms of their interpretation. So we can see this topic here, which is a set of topics that have been extracted by a student of mine around COVID-19 discussions on social media across 5 different countries. And we see the topic here is about masks and hand washing and not touching your face and covering and wearing gloves. So this has, by looking at the tweets associated with this topic, we can say, well, we'll interpret this topic to be mostly about discussions around precautions. But there's no guarantee that the groups that you're identifying, or these latent groups, always make interpretable sense. Like here at this top, in this top topic, there's a number of not very clearly related words. We look at the tweets associated with them, and there's not a very clear sort of theme here. So there's no guarantee that these lower dimensional projections, or these low embeddings, or these low dimensional sort of representations capture a real world relationship that we know about. They could be artifacts of the data, so collinearities in the data, but there's some relationship here. Maybe it's not interpretable, but it may exist. But that's not the only way that you can talk about dimensionality reduction. So another thing that you might be familiar with are these ideas, is this idea of compressed files, so WinZip or zip files, or image compression like PNGs or JPEGs, or audio compression like MP4, AAC, these kinds of things. All of these are also examples of dimensionality reduction, where we have many bytes of data or many byte representation of a particular file or image or document or snippet of sound, and we want to compress that down into fewer bytes. This is also a form of dimensionality reduction, but here you don't have necessarily some latent factor that you're trying to, or latent space you're trying to interpret. Instead, you are giving up or trying to reclaim space at the expense of noise, where we are okay losing something in our compression. We're introducing noise into our compression to get this smaller space or smaller representation. And we'll see a good example of that when we talk about SVD in a few minutes.
Now that we've talked a little bit about how we might interpret this idea of dimensionality reduction in a couple of ways, let's talk about how we might actually implement this using the tools and methods available.
So we've already talked about clustering. This is one way that you can do dimensionality reduction, going from this full square matrix to this potentially thin rectangular matrix with very few clusters for many different elements. One way you've seen this is what we talked about a couple weeks ago with the Gervin-Newman clustering approach, where you iteratively remove edges ordered based on their betweenness centrality and look for a maximal point of modularity, where modularity is the metric of a measure of goodness of your clustering or a particular clustering. We've already talked about min hashing. It's got dimensionality reduction here in the summary, where it compresses a set of documents that are featurized by their shingles or featurized by their words, of which you can have many, down into some much lower dimensional space based on the number of permutations that you've built into your signature matrix. So that's clearly some form of dimensionality reduction, because we claim that the rows in this signature matrix tell us something about this data, or tell us something about similarity in the input matrix, and the number of rows in our signature matrix is much, much lower than the number of rows in our input matrix. And here it's actually a really good example of where these lower dimensions, the signature matrix, doesn't really capture this idea of some latent factor or some interpretable latent space like ideology or genre or product category. Instead, we're looking at trying to preserve the similarity characteristics between documents, and that's the thing that we're going for. Even if we can't necessarily say these two documents had this particular word in common, we can say something about these two documents had a similarity of X% in Jacquard similarity. So we've already talked about this idea of dimensionality reduction that we can answer with graph clustering, and we can answer for sets of or documents that are characterized by sets, or elements that are characterized by like sets of common neighbors. We do that with min hashing. But there are other general methods for doing dimensionality reduction as well. So if we're trying to do decomposition to latent factors, we've talked about that to some degree. Another way to do this is to reduce dimensions where you want to minimize the amount of error you introduce by doing this reduction. So if we want to go back from our reduced dimensional space to the original space, have we lost some signal in doing this reduction in dimension, and can we choose some lower dimensional space that allows us to reduce this reconstruction error as much as possible. So PCA is one example of this, where you take some large feature matrix with many documents across n dimensions. So in this matrix we have x1 to xm different documents, and we have d1 to dn different features. And with PCA, what you do is you break down this feature matrix into a set of components, so principal components, where your first principal component, or the first column in this new feature matrix, is, or rather represents, the axis of most variance. So this is where most of your information, or most of the variation in your documents, is captured by this first principal component. You can break it down into a second principal component as well. There's slightly less variation here, but the variation in this second principal component is separate from or not easily captured by this first principal component. You can actually do this for n components. So if we have n different dimensions, we can have n principal components. This is ordered by the magnitude of the eigenvalues in your data, or in the decomposition of this feature matrix. And if you kept all the components here, really what you've just done is you've rotated your original data set. And with PCA, the goal is, given some data, we want to do this rotation, so then we can project data down into a dimension with the highest variance, or some set of dimensions where, by looking at the first 2, 3, 4 principal components, we've captured as much information as we could capture given any other set or any other projection into those 4 dimensions. So here we take this example with hello, we rotate this space, and then by projecting down into this singular dimension, we can see that we're still able to capture the general sort of variation among the data points, or the clusters of data points in this word, even though we've lost a lot of the height and we can't necessarily see that this data represented hello. We can see that there was good separation, or clear separation, between the letters in our data points. So PCA is one very common method for doing dimensionality reduction.
And you can see an example of principal component analysis at work here in the Module 3 folder of the GitHub repository. And I have an example for SVD as well. So we can think about what we're trying to do here. The goal is to take a large data set, basically a matrix or a data frame, of movies by actors, where we have potentially hundreds of thousands of movies by hundreds of thousands of actors, and represent these movies in fewer dimensions, where the fewer dimensions, or the dimensions that we choose to use, capture something about the structure of the data. And principal component analysis gives us a way to say, well, here are the here are the dimensions that are most important. So this example from the hello visual, what are the dimensions that capture the most variation in our movies? So we're going to use the IMDb movie data set that I've made available to you. We can look at this and see that it's a very large data set. We want to restrict it down a little bit to make some of this data more tractable for us here. This PCA has scalability problems that I'll talk about. So the first way I'll do that is to let us focus just on US relevant titles. So there's an additional data set now that I've added, this US relevant titles CSV file. That's a bunch of titles that have been released in the United States. So this lets us take our data set of movies and actors and reduce it down quite a bit from, I think it cuts it about in half in terms of the number of movies that we have. I'll talk briefly about how we represent this. So one way you might imagine evaluating or representing this data frame of movies by actors is creating a list of lists where you have every element in the first list is in fact a list of ones and zeros representing which are ones for the actors who are in this film. So in this first case, The Other Side of the Wind, you might have a list that contains just 1 and 1 for these first two actors, and then zeros for all other entries. The Naked Monster, this next film, might have the first two elements in this list be zeros, followed by 3 ones representing the fact that these 3 actors have been in this film. And you keep doing that for all of these actors, or all these films. But what should become quickly apparent is that most of these lists, these sublists, are going to be sparse. What that means is they're mostly zeros. Most films only contain a handful of actors. Again, that's not always the case, but this is a general rule of thumb that we'll exploit here. So rather than storing these large sets of lists that are mostly going to be zeros, we can use instead what's called a sparse matrix, which is a particular representation of storing the data, where instead of storing this big multidimensional array, we store a list of elements where each element contains the row and column of a non-zero element in the matrix. So this LIL matrix object is from SciPy, and we can tell it, well, we have X many actors, X many movies, Y many actors, and we're going to say that every element in this sparse matrix is a Boolean, whether that movie contained that actor or not. It takes much less memory to do this, or to do this storage, and then what we go through is for every movie in the list, we then update this sparse matrix, setting the row and column to 1 if this actor is actually present in this movie. So this gives us a way to represent this matrix in memory much more efficiently. This is where you see this example. And now we just create a data frame from this, and we have 102,000 rows by 162,000 columns. So almost 100,000 movies, almost 160,000 actors who have been in these movies. Now the next thing I want to do is reduce the number of columns in this data a little bit more so we can deal with some tractable analysis. So what I want to do is I want to take the top 1,000 most frequent actors. So this top K actors variable, I just set that to 1,000. You can download this data set and play around with that value if you want to use more actors or see fewer actors. And in this next cell, I will sum up the data frame across the columns, or I guess across the movies, which gives me sums for every column. That tells me how many times a particular actor has showed up in this data set, and then I can create a set of actors by sorting this summed series, taking the top K highest or most frequent actors, and creating a set containing just those actors. Then in the next cell, we take our data frame, our original data frame, and reduce it down to just those top actors. And we have to do one more step to make sure that we're not keeping movies that don't have any actors from this top K set. So that's what these first two cells do. And we can see we reduce this data set down quite substantially, going from 100-odd thousand movies to now just 18.5 thousand movies, and our 1,000 most frequent actors. Like I said, you can evaluate or tweak this top K actors value to some other larger or smaller value. to explore what this might look like with more actors. And in fact, we'll do that when we get to SVD. But PCA has some scalability issues that prevent you from trying to, or that make it difficult to apply to very, very large data sets, which is part of the value of SVD that I'll get to. All right, so now what we want to do is apply PCA to this matrix of rows, or of movies and actors. So we take the PCA object from sklearn's decomposition package. I have a link to the documentation here, and we apply it to this matrix. So the documentation is pretty clear. We could run it without any arguments. The main argument that we care about here is this in components argument or parameter. We want to use this in components parameter to say how many dimensions, what is our reduced dimensionality for this matrix. So here we're going to set that to 2 just for example, or for illustrative purposes, because we're going to do some visualization from this data. But you can set it to whatever value you think is reasonable. That could be driven by your use case, or if you go back here, actually there is some methodology in sklearn that optimizes what are the most reasonable, or what's the most reasonable number of components here. All right, so here at the bottom, we instantiate the PCA object, set its components to 2, and then we call .fit using this matrix. I'll mention here that I have this matrix underscore dense object that I pulled from the data frame. This is essentially going from the sparse matrix that I showed you to this dense matrix that is in fact represented as though every element or every row is a real list of zeros, or zeros and ones. So this dense matrix can take up a good bit of memory, which is partially why I employed this top K actors filter, because if you try and run PCA on the sparse matrix, it'll fail. There's an example of that in the code here in a second. But if you try and make a dense version of that sparse matrix without any sort of filtering, you very quickly run out of RAM. All right, so we now have this fitted PCA object that's set to 2 components. You can call PCA.transform on your matrix to get back this reduced copy, or this reduced dimensionality version of the matrix. And here, if you look at mp.mean, that's the mean function, or the average function from NumPy. We take this reduced matrix, and we see it's got just these 2 dimensions. The average across all the movies in this data set, this 18,000 movies, is very close to 0. But we can visualize where these movies get placed in this 2-dimensional reduced space. We see about maybe like 4 different clusters here. We can do some inspection very quickly by taking the reduced matrix and keeping only those elements where the x value is greater than 1 and the y value is greater than 0.8. That gets us these few movies here in the top right. And we print out just what are those movies and what are the genres and actors in them. Or what are the genres and actors associated with that movie. We see there are a few, they mostly look like action and drama with Eric Roberts, Michael Madsen, and a few other people. We can look instead at this cluster of movies down in the bottom left, where we take this numpy.argwhere, which essentially says instances where this Boolean matrix reduced is less than 0.1, which says in this matrix, this reduced matrix, where do we see the x coordinates being lower than 0.1? We end that with the y values in this matrix being also lower than 0.1. This gives us this little square down here at the bottom left. And we can look at what movies are there as well. And we see a different set of movies, Grizzly 2 Revenge with George Clooney, Charlie Sheen, Crime and Punishment, a different set of movies and actors. That's not hugely informative, but we see there is potentially some structure here. So what we may want to do next is see, in a particular one of these clusters, who are the actors who are most represented, or what are the genres that are most represented. So here we go back to looking at this top right cluster. We take out all those movies, and rather than printing out the movies and actors, we just sum up which are the actors and movies that are present here, and we print out the top 10 most common genres and actors. And we see action, drama, and crime movies are here, primarily with Michael Madsen and Eric Roberts. Just to refresh your memory, Eric Roberts is a an actor who has been around for a long time. He's born in the 50s, but crucially, he's been in about 700 films or 700 movies and TV shows. So he's a prolific actor in the space, which may make sense about the principal component potentially extracted here isn't necessarily genre, but whether a movie contains Eric Roberts or not. Because here in this bottom right, we apply the same sort of extraction when we look at the most common actors and genres in this bottom right cluster here, and we see Eric Roberts is in these movies 31 times. Michael Madsen's not near as common, so maybe what we're seeing is the presence of Eric Roberts being one of the major drivers of these films. And we'll actually see an example of that in the SVD example. We can do the same thing looking at the bottom left. So now we look at the top right, bottom right, and we look at the top left, or the bottom left rather, and we see that Eric Roberts is not is not well represented in this set of actors. Instead, we see Joe Hammerstone, Tony Devon, Nick Cage, and a few other people. This is conspicuously Eric Roberts is absent from this set of films. That gives you some structure there. We'll actually use that structure when we talk about clustering in the next module. But just as we have seen in the Jacquard similarity in the movie set in the past, you can do the same thing looking at movie similarity in this reduced dimensional space. So here, for example, if we take the Lord of the Rings, the Fellowship of the Ring, go to this reduced matrix, we see that the value for that film is close to 0. But we can look at the pairwise distances here. And using the pairwise distances with the Euclidean distance metric between the reduced matrix and this single query, or the entry for this single film, Lord of the Rings, we can actually rank out what are the top 10 most, or here are the top 20 most similar movies to the Fellowship of the Ring in this reduced feature space. So it's not necessarily which ones are the most similar sets of actors, but projected into this two-dimensional space that appears to be primarily about whether the movie includes Eric Roberts or maybe Michael Madsen. We see the movie that's most close to the Lord of the Rings is The Survivor, followed by Hail Caesar, followed by Safe House. So maybe this isn't enough dimensionality to capture, real similarity for us. So we could increase the number of dimensions here. So you could go back to PCA and set the number of components from 2 to 8 or 20 or 64, and you'll get a different ranking here. Just like with PCA, where we said we want the 2 components that have the highest variation, here we can do a similar kind of thing and say we want the top K components from SVD that capture the most variation. To do that, we can just set this S sub R value to 0 in this diagonal matrix, which has the effect of zeroing out these other rows and columns of the U and V matrices. We can sort these dimensions by the magnitude of these S sub 1, S sub 2, S sub 3 values to tell us which are the most important dimensions, or what is the order of the most important dimensions that we want to keep.
Let's talk about how this works. For SVD, we have some matrix A of m rows by n columns, and it can be reduced into these 3 different matrices. A is some input matrix. For example, now we'll talk about m documents and n words. U is what's called a set of left singular vectors of m documents and R concepts. We're going to talk about interpretation. Sigma is our list of singular values, diagonal matrix, where all values all cells except for what's on the diagonal are 0. And we say this represents the strength of each concept. And then V is this right singular, or set of right singular vectors associating terms with concepts. So U associates documents with concepts, and V associates terms with concepts. And you can think about this kind of graphically. We have this potentially tall rectangular matrix A that we can represent by 2 skinny rectangular matrices and 1 square diagonal matrix. From SVD, an important property here is that it's always possible to decompose any matrix into this set of U sigma and V transpose. And U sigma and V will be unique, given that, remember that sigma is this diagonal matrix, the values along this diagonal are going to be positive and will be sorted in decreasing order. So S1 is going to be the largest singular value in this matrix. And we can think about this, we can ground this interpretation in an example when we talk about movies or users to movies. Say this matrix A represents rows for users and columns are movies, and cells represent ratings, or how much I liked a particular movie, or how many times I've watched a particular movie. You can replace this with any other sort of representation you want. It could be politicians and domains that they've shared, or people in the product categories or products they've purchased from Amazon. All kinds of representations here. So we'll ground this in this user to movies example. So we have this matrix A of users and the movies they've watched and how many times they've watched them. For instance, we can decompose this into U sigma and V transpose, where we say the U and V matrices capture the concepts underlying this set of movies or these set of users, where U relates users to the latent sort of genres of these movies that are interesting to them, and V represents the relationship between movies and the genres in which they're from. So we can ground this into what this actual decomposition may look like of U sigma and V transpose, and we say that this potentially this first column of U is called or represents the sci-fi concept. This middle column of U represents the romance concept, and this right column of U maybe captures some noise in variation of the data. So what this says is this first user in the first row, has a interest in the sci-fi concept of about 0.13. Maybe it's not necessarily clear how high that is, or whether that's high or low, but we can say that that's a high value for that row. So that user clearly seems to be more interested in the sci-fi concept than they are in the romance concept. This strength value, or this first value in our sigma matrix, tells us how strong this sci-fi concept is, or how much variation there is in this sci-fi concept. And we can use this V matrix, or V transpose, as the movie to concept matrix in the same way that we had the user to concept matrix before. And this says, or maps which concepts are most strongly associated with which movies. So here we can see that the movie The Matrix, Alien, and Serenity all have high scores for the sci-fi concept, which makes sense if we think about what those movies are. So we can talk about an interpretation of SVD as decomposing a data set, our A matrix, into a set of maps. So this first U matrix maps users to genres of interest or some kind of latent concept or latent interest in the data. This V matrix maps our features, in this case movies, to what those concepts or latent features may be. So in this case, genre. And the sigma matrix tells us, well, how strong or how much variation is there among the different latent factors or latent dimensions that we talked about or that we've identified.
The nice thing about SVD that I mentioned is that it's more scalable when we're dealing with sparse matrices. So we couldn't deal with sparse matrices with PCA, meaning that we had to reduce our feature space into something that was more tractable. Here we can work directly with sparse matrices, or SVD is scalable if we only care about the first k singular vectors, which translates to the first k components that we set when we did PCA. So now we can talk about an example here. So remember in PCA we set n components equal to 2. With SVD we essentially can do the same thing. We instantiate the truncated SVD object from sklearn's decomposition package, just like we did with PCA. Has a very similar set of parameters, and we can reduce this down to 2 dimensions, just like we did with PCA, and we get a similar kind of structure where we get what appears to be 4 different sets of groupings of movies by actor here. And again, this is the 18.5 thousand movies by 1,000 top K actors case. In the description for SVD, we talked about we have a matrix U that connects the movies to this latent factor space, this R space, this lower dimensional space. But we can also use the V matrix to understand something about the connections between the features, the actors in this case, and this concept idea, or map the strength of these actors into, or map these actors into their strengths across these different concepts. So in SVD, there is an attribute of the fitted SVD model called the components. We can see here it's 2 by 1,000. So 2 is the the dimensionality reduction that we asked for, and 1,000 is the original feature space. And now we can say, well, rather than querying for films and evaluating who are the most, or which films are the most similar across these different films, we can do the same thing with actors. And if we pull out here this actor with George Clooney, we see his strength across these different factors is mostly 0. He's stronger on the second dimension than he is in the first dimension. And we evaluate the similarity between George Clooney and other actors. We see he's in this space most similar to Lalu Alex, Steve Carell, Liam Neeson, Gerard Depardieu, and others. You could do the same thing actually with Eric Roberts, and you would see that Eric Roberts is going to be high in the or has going to be a high value for that first dimension that generally associates to whether Eric Roberts is in a film or not. PCA can also do this. You can do the same kind of thing with PCA, but as I mentioned, PCA has some issues with scalability. So as I already said, if you try and fit PCA to a sparse matrix, it fails out and says try truncated SVD instead. So if we look at this sparse matrix, rather than the 18.5 thousand movies by 1,000 top actors, we have 102,000 movies by 162,000 actors. We can apply truncated SVD directly to that sparse matrix, and we see a different structure emerge. So rather than the 4 different groups that we had before, which may be associated with whether a movie had Michael Madsen or not, and whether a movie had Eric Roberts or not. Now we have a little bit of a different structure. We have this one cluster on the right, and some cluster on the left that gets spread out up into, spread out vertically around x equals 0. So it's not as clear of a relationship or set of relationships, but we have many more actors here. And you can do the same kind of thing in evaluating distance between movies and distance between actors that we did before, but now we have many more films and actors to do that in. So now we've talked about connecting the idea of dimensionality reduction with the interpretation of latent factors, and you have seen a couple of different methods for doing that using PCA or SVD. There's Menhash that we talked about before, which you can think more of as a compression mechanism than this latent factor idea. The point behind telling you all of this is it helps us, or it will help us when we get to clustering next time. Because as I mentioned last time, when we're talking about very high dimensional spaces, the distance metrics sort of break down in value. But when we can compress or reduce the dimensionality of our data into a fewer number of dimensions and still maintain as much structure about the original data as possible, we can get better sets of clusters when we actually do or apply our clustering algorithms, which we'll talk about next time. If you have any questions about any of this, or you want to see additional examples or run through the PCA or SVD examples with me, by all means, come to office hours, or you can post in the discussion forum or reach out to me via email.